Materials. I used 4 9-volt batteries, aluminum foil, 0.5 millimeter pencil lead, and 2 alligator clips. Set up my demo, I used 4 9-volt batteries and put them in a series circuit. A series circuit means that the voltage actually adds up, so I had 36 volts, whereas in a parallel circuit, which is a common circuit, it would still only be 9. Then I attached the alligator clips, and I'll talk a little bit more about how that worked later on. So at this point I closed the circuit, and the graphite conducted the electricity, and the gas around the graphite was ionized and plasma was formed. A little ball of plasma at the end of the graphite was formed and cut right through the aluminum. Both the graphite and the aluminum were consumed in this circuit. As you can see, I ran out of graphite about halfway through. And if you see how bright it is, this process was actually used in the early form of light bulbs. It's called a carbon arc electrode. How do plasma cutters work? On a very basic level, so much energy is channeled through such a small space that it heats up very intensely, and it ionizes the gas surrounding that space, so typically air. So the gas is ionized, meaning that the electrons on the atom gain so much energy that they physically leave the atom, remaining just an ion and a whole bunch of electrons floating around. So the states of matter, it's actually, plasma is considered the fourth state of matter, where gases go from just a normal gas to plasma when they gain enough energy. So plasma cutters kind of like force energy through a point to create a little ball of plasma that will cut through very strong and heavy metals very effectively and efficiently. For my demo, I made a baby plasma cutter using just pencil lead and batteries and aluminum foil. So how I did it was I created a circuit, an open circuit. So I attached the positive end, the red alligator clip, to the pencil graphite, and the negative end to the aluminum. And both ends were attached to their respective ends of the battery pack I made. And the circuit was open because there was no conductive path from the positive lead to the negative lead. So there was no current flowing through, but there was potential for a lot of current to flow through. And what ended up happening was, as the graphite got closer and closer and closer to the aluminum and nearly touched the aluminum, a conductive path was created. So the circuit was completed, and all of a sudden a whole bunch of electricity was flowing from the batteries to the graphite. And by its nature, graphite is extremely conductive, just because of its structure. And as enough energy passed through the graphite, it was such a small point of contact because it was 0.7 milliliters. There was hardly any resistance, and it was a very concentrated amount of energy. The carbon in the graphite was ionized, so as a result, all the electrons left, and there was carbon atoms, and a small ball of plasma actually formed. This plasma was so conductive by its nature that it vaporized the material around it and cut straight through the aluminum. So both the graphite and the aluminum were consumed in this circuit. Yeah, so that's how my mini plasma cutter worked, and it kind of represents how a larger plasma cutter might work on a very industrial scale. So now I'm going to talk a little bit about the math behind my demo, specifically the combustion of aluminum. The equation for aluminum to aluminum oxide, and I'm going to balance it, so this becomes 4 moles of aluminum plus 2 moles of aluminum oxide plus 2 moles of O2. So that's the balanced equation. And I already looked up the enthalpy of the equation, which is negative 1,675 kilojoules per mole. So now what I'm going to try to find is the energy released by the combustion of the amount of aluminum I burned. So first I have to find the amount of aluminum I burned. So I'm just guesstimating. I'm guesstimating I used roughly 0.1 centimeters times 0.1 centimeters for the area times the thickness of 0.01 centimeters to get 1 times 10 to the negative 4th centimeters cubed. Then I found the density of aluminum. I looked it up, equals 2.7 grams cubic centimeters, and the molar mass of aluminum foil, which is a little different than aluminum because aluminum foil is only 99% aluminum. So as a result, it's just a little bit heavier. It's 27.00 grams per mole. Okay, so now I have that. First, I took the volume of aluminum and I multiplied it by the density. So times 2.7 grams per centimeter cubed to get grams of aluminum. So I got 2.7 times 10 to the negative 4th grams of aluminum. Then I divided that by the molar mass. 27.00 grams per mole to get moles of aluminum, which was 1 times 10 to the negative 4th moles aluminum. That the enthalpy is this number, kilojoules per mole, times the number of moles of aluminum that I used. And when we multiply these two numbers together, we get 0. Negative, because it's a heat was released, obviously, so it's exothermic. Negative 0.1675 kilojoules. And this number is important because it goes into the heat of reaction. So now that I've found the heat it took to burn the aluminum, I can start to have a better guess of the total heat that was put into the reaction. By the basic laws of thermodynamics, for all the energy that's put into a system must somehow either stay in the system or be released out into the system, but it's neither created nor destroyed. So the energy put into the system via like batteries was transferred via the plasma, the excited electrons, to either burn the aluminum or oxidize the aluminum, or was conducted into the aluminum that was not consumed. So as the reaction happened, the whole sheet of aluminum foil got hotter, and that this number right here would account for that, plus this interesting rate law. And this rate law accounts for the specific heat of all of the aluminum oxide made. So as this reaction happened, particles of aluminum oxide were produced, and these particles got hot and they held heat. And this right here, this equation accounts for that heat. All of these numbers added together